Swayam Prabha. Digital India. Educated India.
Let us look at some of the simple methods now. So, what we have discussed now, two methods of measurement, gravimetric and volumetric. We have looked at what are the different types of errors that can creep in. Now, we should look at how do we do the measurement in volumetric manner and gravimetric manner. Volumetric manner, it is very simple. Simplest is burette method, and you can of course automate it. Okay, and then there are turbine type of flow meters. I will be discussing only these two. Okay. So, this is burette method is very simple. It's one of the simplest methods of measuring the volumetric fuel consumption. This uses a glass burette. So, all of you must have seen the glass burette in first year of your engineering chemistry labs, you must have seen burette. So, these are long tubes which are graduated, okay, and you can measure, basically take a stopwatch. If it is a 50 ml, you can measure, okay, from start to the stop, 50 ml, how much time you take, okay. So, that is what you can do, or you can say 20 ml, 20 seconds, how much fuel is consumed. So, there are many ways in which you can do the measurement. This is also some kind of a simple device, in order to make it more accurate, instead of having a linear measurement, you can have a vessel of 100 cc. And there could be one mark here and there could be one mark here. So, you start your stopwatch when the fuel is here, and then cut off the other supplies. So, only from here the fuel is going to the engine, and you start the stopwatch here and stop the stopwatch here. So, you know how much time your engine has taken in consuming 100 cc of fuel, and that you can use for finding out the fuel flow rate. Okay, so, time taken by the engine to consume this volume is measured by stopwatch. Volume divided by time gives you the volumetric flow rate, and then you can of course multiply it by density to get mass flow rate of the fuel. Okay. So, to avoid the error in citing fuel level against mark of the burette, photocells are used. So, basically what is done is, if you want to automate this automatic burette, what you do is you put a photocell here. So, photocell will be throwing the light. As soon as the level dips below, it will give a signal. So, you know what time it has started, and similarly what time it has stopped. So, one photocell here, and that way the manual response time, because when you see and when you press the stopwatch, there could be difference, manual error. That can also be avoided by making it automated. Okay. You could have 20 ml flasks, 200 ml, 50 ml, whatever you want, you can measure and make a device of your own. Okay. So, this is very simple burette method. Next is turbine type of flow meter, and what happens is, in this there is a turbine wheel, that is small turbine is located here, and there is a magnetic pickup. So, magnetic pickup is basically picking up when the pickup is there, when the blade of the turbine passes through it, it generates one pulse. Okay. So, when the fuel flows, obviously this turbine will rotate, and what is the rotational speed that is picked up by the magnetic pickup, and it is going to a unit which knows that, okay, if it is operating at this speed, this is the flow rate. It is pre-calibrated device actually. Okay. So, it consists of a turbine which rotates due to fuel flow. A light beam is interrupted by blades of the turbine. So, you can have either magnetic pickup or optical pickup. So, if you have a optical one, then you can use a light beam. Okay. The resulting signals are counted and the volumetric flow rate is displayed digitally. So, this also measures the volumetric flow rate, no mass flow rate. Okay. A rate mode can be selected to give a total flow rate. Bypass line is used to reduce the effect of pulsation in the fuel line. So, this is how a turbine flow meter looks like. Okay. Now, what is the advantage? Advantage is it is simple, it is durable in structure, It is easy to install because it's not very big. Okay, burette is very big, but this is very small. Turbine meters are able to operate under wide range of temperatures and pressure, and there is very low pressure drop because it is not stopping any flow. It is not having constricted passages, so there is no pressure drop. It is most effective in applications with steady and high speed flows. So as I said, it in unsteady flows, this is not going to work. But if you have steady flow condition, this is one of the most beautiful device to use. It's quite accurate. Disadvantage, it requires constant back pressure in order to avoid cavitation. Okay, so constant back pressure means there should be sufficient pressure upstream. Downstream, if the fuel consumption is more, there may be some cavitation. So that can really lead to errors. And its accuracy is adversely affected by bubbles in the liquid. So you should not have any bubbles. And it is sensitive to change in fluid viscosity. Okay, so these are the three negative aspects of flow meter. So this is all as far as the volumetric flow rate measurement is concerned. Now let us look at gravimetric fuel flow measurement. How do we do gravimetric fuel measurement? So please understand, this is a device. Okay, there is a vessel which is having fuel. Okay, and this is the this is like a what you call weighing balance. So this is a pivot here. So counterbalance is this is tare weight. Tare weight means this is equivalent to the weight of the container. Okay, and here you could have either measuring bed. Normally nowadays people put load cells. Okay, and here you see what is happening. The fuel is coming in from the tank, and fuel is going to the engine. Now if you look at the engine, for example, if you look at diesel engine and if you look at diesel injectors, not all fuel that you are putting in the engine injector is injected in the engine. Some fuel is returned back. So if you put it back in the tank, but if you don't put it into this device, then what will happen? It will be counted towards consumed, but it is not actually consumed, it is coming back to your tank. So if you want accurate measurement, you have to put it back here. So the engine from the fuel from the engine will come back here. So basically the changes in the mass will be equivalent to the fuel that is being consumed by the engine, because what is going out and what is coming back, both are put here. Okay, and then of course there are some pumps and other things, and instantaneously from the load cell reading you will know what is the consumption rate. So automatic fuel measurement system consists of a fuel balance, contactless control light gate, a measuring vessel, tare weight, and switching unit. These are the components of the gravimetric fuel measurement system. Fuel from the fuel day tank. Day tank means basically tank where the fuel is stored all the time. Or fuel supply line flows via a solenoid valve. So this is the solenoid valve. So when you do the measurement, solenoid valve stop the supply, so that you know how much is the change that has taken place. Okay, into the measuring vessel suspended from the balance beam. Solenoid valve control is controlled by the control unit. Measuring cycle in the gravimetric consists of three phases. First is that it will fill up the measuring vessel. When you want to start the measurement, first it will you fill it. Okay, then engine uses up the pre-run quantity of the fuel. Then engine uses up measuring quantity of the fuel contained in the measuring vessel on the balance. So basically once it is filled, you just stop the supply and then see how it is changing. Once the fuel supply from the tank is disconnected, then the change will be equal to what is being consumed by the engine. So 20 seconds or 50 seconds it can measure how much is the change in the weight. So now it is measuring the change in the weight of the fuel, and then do the calculations and finally display what is the kilogram per hour or kilogram per minute, gram per minute fuel consumption that is being done by the engine at that particular load and speed condition. Okay, does it make sense? So time for predetermined amount of fuel is determined only in the third phase. First two phases are preparatory in nature. The diet of an engine consists of so this is the gravimetric fuel consumption. So now let's also talk about air consumption. So, what is consumed by the engine is fuel and air. For finding out the performance of the engine, accurate measurement of both is essential, and we have already seen how do we accurately measure the fuel. Now, let us see how do we accurately measure the air. So, in engine, first you should understand, when do we take the air in? Only in the intake stroke. So, for the 3 strokes, intake valve is closed, right. Even in one stroke of the engine, in the intake stroke of the engine, what is the rate at which is air coming in? Is it same or is it changing? It is changing, because in the beginning the rotational speed is constant, but piston linear speed 0 to very slow speed, then in the mid stroke it is fast, and then again at the end it is slow. So, in the beginning there is very small vacuum, when it is fast the vacuum is more, and again it is slow. So, the air suction velocity is also changing. How do we measure the air flow rate? Normally in a non-engine experiment where you have continuous flow, using orifice plate. So, you have an orifice plate, and that orifice plate makes a vena contracta, and then across that you put a manometer. It could be, if the vacuum created is large, then you put a U-tube manometer. If it is not large, you put more accurate inclined manometer. That is simple thing, right. But can you do that in the engine? Can this be done? The answer to that is, it cannot be done directly. Why it cannot be done directly? Because even in a multi-cylinder engine, the nature of engine air, the air flow will be pulsating. It will not be steady flow. The method which orifice plate method which I told you, it is applicable only when the flow rate does not change, it is constant, right. So, in IC engine application, for satisfactory measurement of air consumption is extremely difficult, because the flow is pulsating due to cyclic nature of the engine, and because the air is a compressible fluid, that also, okay. Therefore, the simple method of using an orifice in the adduction pipe is not going to give you a satisfactory result. In fact, the manometer will all the time keep on dancing, it will not get enough time to stabilize, right, because of the pulsating nature. All kinetic flow interfering systems such as nozzles, orifices and venturies have a square law relationship between the flow rate and differential pressure, which gives rise to severe errors, because differential pressure will keep on changing all the time because of the fluctuating nature, and therefore you will have severe errors in the unsteady flow. So, unsteady flow of the intake air in the engine makes our life extremely challenging. Pulsation produced errors are roughly inversely proportional to the pressure across the orifice for a given set of flow conditions. Okay. So, how do we measure? So, we measure it, we still use the same method, but we try to kill the pulsations. How do we kill the pulsations? Suppose I have a big engine of single cylinder engine of 1 liter capacity. Okay. So, 1 liter so let me ask you this question. If there is one single cylinder 1 liter engine versus a 1 liter 4 cylinder engine, which will have higher air pulsations? The single cylinder engine or 4 cylinder engine? In this case it is 1 liter 1 cylinder, in this case it is a 250 ml 4 cylinders. Its total volume is swept volume is same. Single cylinder will give you large pulsations. Okay. So, in order to overcome or do away with the pulsations, what you do is you take a box of roughly 200 to 300 times the capacity of the swept volume of your cylinder in case of a single cylinder. So, for the 1 liter engine, you will have a tank which is 200 liters, and then what you do is in the bottom you make a section, you cut it, and there you put a flexible rubber diaphragm, okay, tube. Basically you take a tube and then stitch that so that there is no leakage, but if there is pressure pulsation, this diaphragm will go up and down, so that the pressure more or less remains same, okay, and it has a large volume 200 liters, 300 liters, and then at the end entry you put a orifice plate like this. So, you have this tank and this is the orifice plate that you have put, and here this is connected to the engine. So, although the air that is coming in will be pulsating, but this pulsation is going into a very large volume. Okay. So, there will be some vacuum created, but the value will be very small, and there will be some diaphragm somewhere on one side that will also avoid this pulsation. And then here you have the orifice plate. So, when the engine starts, the airflow from the orifice will be more or less steady, the pulsations will be gone, and here you put a U-tube manometer. So, inside pressure, that is here, and outside pressure, of course, atmosphere. So, this U-tube manometer is going to give you the height difference or pressure difference, and you know what is the diameter, and then simple formula for the airflow can be applied here. So, this is air box method. So, this orifice method can be used if pressure pulsations is damped out by some means. The usual method of damping out pulsation is to fit an air box of suitable volume of the engine to the engine with an orifice in the side of the box which is far away from the engine. So, this is how you do the measurement. Yeah.
The mass flow rate of air will be changing because there will be more pressure loss in this part.
There will be no pressure loss. There will be no pressure loss. Why there will be pressure loss? This is open. This is having a significantly big diameter. Okay. If you are putting a very small orifice, then of course this will be more, but then this will be constricting the passage. So, you suitably choose the diameter of the orifice, so that you get this engine should not get choked. So, there is no pressure loss here in the tank, and it is quite large, it is 200 liters, and you are taking only 1 liter at a time. So, that you take in one stroke, and remaining 3 stroke engine is not demanding any air, but the air is coming in slowly into the tank. So, it is being sucked in one stroke, and from here it is coming continuously. I will demonstrate that to you in the lab. The second is that laminar flow element. So, one of the other ways, here what happens is that if the air is having some kind of a turbulence, then the measurement will be inaccurate, because if you look at the orifice plate theory, one of the assumptions in orifice plate theory is that the flow has to be laminar. Okay. So, here this is not going to give you a very accurate result. So, the other thing that you do is that you put a laminar flow element instead of having a orifice here, just this orifice plate, you put a laminar flow element. Laminar flow element is also same. What happens is that this air comes in, there is a filter of course to remove the particulate, and then there is a honeycomb. Okay, what is honeycomb? So, basically if you take 200 straws and you allow the air to flow in, whatever turbulence it may have here, but once it comes out of through that honeycomb, it will be laminar in nature, and then here you can put a orifice plate, and then you can have an inclined manometer or something. So, orifice plate is actually put, if it is put after the honeycomb, once you have ensured that the flow is already made laminar, then the flow will be measured more accurately. For example, here the flow is made laminar, and across the orifice plate you are measuring the differential pressure. Okay. So, this is called laminar flow element. The next is, we are interested in measuring the power output of the engine, that is called brake power output. So, let us first understand the principle of power measurement, and then we will apply that to different types of dynamometers for power measurement. So, the brake power measurement involves determination of torque and angular speed of the engine power output shaft. We know if we have to measure the power output, how do we calculate the power output? What is the formula? The P equal to 2 pi NT. P is the power, N is the speed of the engine, and torque is T is the torque. So, the brake power measurement involves the determination of torque and the angular speed of the engine output shaft. The torque measuring device is called dynamometer. So, whenever you hear this word dynamometer, so you will immediately say that this is nothing but a torque measuring device. Okay, and you know how to measure the speed. So, once you know the torque and you know the speed, you can calculate how much will be the power produced. Power produced means brake power produced by the engine. Okay. So basically the principle is that this is the rotor. Rotor means shaft. Shaft is rotating. Okay, and this is the stator. Okay, stator means it's fixed. So this is what is the shaft, and this is connected to a hinge or something. And then when this shaft rotates, what will happen? This will apply force on the stator, right? So when this applies the force on the stator, you have an arm here on the which is attached to the stator, and then there is a balance that is attached here. Okay, and so there is this arm from here to here, this is length is L, and this is the reading on the, because this is being pushed down, shaft is rotating like this, so obviously this will be pushed down. Okay, and there will be some reading here depending on how much force is being applied. So suppose the reading is S. Okay, so the dynamometer can be classified into two main types: power absorption type and power transmission types. So power absorption types means that the engine produces power and dynamometer entirely absorbs that power. And power transmission types, that means it does not absorb power, it transmits it, but it only measures the torque. Okay. So a rotor is driven by the engine under test, and then it is electrically, hydraulically or magnetically coupled to a stator. So how it is coupled? It could be mechanical coupling, it could be electrical coupling, it could be hydraulic coupling. Okay. So for every revolution of the shaft, the rotor periphery moves through a distance 2 pi r. Suppose this is r, so for every revolution rotor will move by 2 pi r, that is the periphery, against the coupling force of F. So this is the force F that is being applied, hence the work done per revolution will be, this is the force, counterbalance force, and it is rotating 2 pi r distance. So what will be the work done? Work done will be 2 pi rf, right, and that will be equal to, so the external moment, again the same figure, the external moment or torque will be equal to S into L, force into distance, torque is force into distance. So the moment balance, these two moments balance each other, so this is R and the force is F, right, and this distance is L and this is S, so S into L will be equal to R into F. Okay, so the work, what is this W equal to 2 pi RF, so work done per revolution will be 2 pi SL. Okay, so work done per minute will be 2 pi SL into N. N is what? RPM. Okay, N you measure in RPM. So the power output will be given by 2 pi NT. Now what we will do is we will apply this, so this is basic measurement principle, whatever will be the dynamometer. Now we will apply it to different types of dynamometer. So let's first understand the absorption types of dynamometer. So absorption type of dynamometer measure and absorb the power output of the engine with which they are coupled, and whenever they absorb power, if you are absorbing power, something will be generated. What is that something? Heat will be generated, right? So that if you don't remove that heat, what will happen? Machine will burn. Machine do not have infinite heat capacity. It has limited heat capacity. So that power that is being absorbed, which gets converted into heat, needs to be removed in order to, for the system to survive. Okay, so that needs to be removed as heat. So dynamometers, there are 4 main dynamometers that I will be discussing with you. One is and these two, first two are basically of only historical in nature, nobody uses them. But if you want to do a testing and very cheap, you don't have money, still you can make these dynamometers on your own in your own workshop and do your experiments very, very cheaply. Okay, as I said, you need some Obviously these will be having less accuracy, but they will do the job, they will still do the job. So one type of dynamometer is called Prony brake dynamometer. Brake, that means you are applying brake. When you apply the brake, you absorb the power and that is converted into heat. The same thing happens in the vehicle also. When you apply the brake, what happens? The brakes absorb the kinetic energy of the vehicle and it is converted into heat. So that's why it is called brake. Similarly, there is something called rope brake dynamometer. Rope brake really means that ropes are used to measure the power output. And then there is hydraulic dynamometer, then there are eddy current dynamometers. So these are 4 examples of absorption type of dynamometer. We will be describing them in detail and understanding them. A transmission of type of dynamometer, the power is transmitted to the load coupled to the engine after it is indicated on some kind of scale. So here you are not absorbing the power, you are allowing the power to go out, but before it goes out, you want to measure it. Okay. So these are also called torque meters. So basically they are just measuring the torque used and by some kind of strain gauges, etc. So let us understand, this is the Prony brake dynamometer. Very simple device. This is the shaft that rotates. It could be a shaft, it could be a flywheel. Normally it is a flywheel of very large size. So this flywheel rotates and these are 2 wooden blocks, okay, brake blocks which are mostly made of wood. And then you have some support by which you try to squeeze that flywheel, okay. And then here you have a torque arm and here you have some weight hanging, okay. So suppose W weight is hanging and this distance is L, okay. So one of the simplest method of measuring the brake power output is to attempt to stop the engine by means of a brake on the flywheel and measure the weight of the arm attached to the brake that will support. So the Prony brake works on the principle of converting power into heat by dry friction, okay. So you are trying to squeeze the flywheel with 2 wooden blocks and there is no lubrication present, because if you put lubrication it will defeat the purpose, you will not be able to stop, that is not the idea, okay. So it consists of wooden block mounted on a flexible rope or band. The wooden blocks, when pressed into contact with the rotating drum, takes place, the engine torque and power is dissipated in the frictional resistance. So when you squeeze it, the heat will be generated and it will be dissipated in the wooden block. The whole of the power is absorbed by converting it into heat and the brake power therefore is given by 2 pi nt. The torque here, you see what is the torque here being generated by the flywheel? That will be the weight multiplied by the length of the arm, W into L. So basically T equal to W into L and N you can measure and you can measure what is the brake power being generated. Obviously this will not be a very scientific and modern method, okay, because if more heat is generated, wooden blocks will start burning, at least some things will start happening, okay. So this is purely from historical perspective, when the engine used to be like 4 meter tall at that time, people used to make these kind of devices. They are no longer used. In fact, I don't think I have ever seen this dynamometer in my life, even in the museums, okay. But I have seen this one, okay, and this is called rope brake dynamometer. So here the idea is that you have some kind of a flywheel, okay, which is attached to the shaft, okay, and then what you do is, flywheel is having flywheel is like this, and this rotates, okay. So this is the flywheel, and then on top of it what you do, you put certain ropes. So this is connected to a scale and this is connected to a weight, Okay, you can see this here also. So these are the ropes here. Okay, so this will going to take couple of rounds or 3 rounds, and then here you have the weight. Obviously this surface has to be quite smooth. Okay, and so when this rotates, this weight is going to act downward. Suppose this is rotating like this, so this will try to lift this torque will try to lift this weight, but this weight is quite heavy, it will try to pull it down, and so there will be struggle, and whatever is the difference that will be seen here in the scale. So the net force being generated will be W minus S. Okay, and you know what is the diameter, so you can figure out what is the torque. Okay, so here on this whole surface, this smooth surface, the rope is stationary, the drum is moving, and the friction between the rope and the drum surface is what is trying to stop, right. So the heat will be generated because ropes are also not that smooth. So the heat will be generated, so the entire energy is dissipated and it is absorbed by this drum, and you can't allow the drum to get overheated, because if it gets overheated, it will start burning the ropes, right. So what you do, you put cooling water inside the drum in here, while making sure that the ropes are not wetted out. Okay, so you put the water in, and there will be some kind of a drain mechanism, and what it will ensure is that this whole thing temperature is kept under control. So the brake is another simple device for measuring the brake power of an engine. It consists a number of turns of rope wounds surrounding the rotating drum, which is attached to the output shaft. One side of the rope is connected to a spring balance and the other side is to load, which you know how many kilograms you have applied. Okay, the power is absorbed in friction between the rope and the drum. It is not accurate because friction coefficient of the rope changes with temperature. So brake power in this case, what will be the torque here? Torque will be W minus S into D, right. So this will be not D, R. So this will be 2 pi, so brake power will be 2 pi NT, N is here and T we have replaced with D by 2 into W minus S. Okay, so now you understand how we measure this, the whole thing works. Okay, so this is the D is the brake drum diameter, W is the weight in newtons, and S is the reading in the scale. So that's how a rope brake dynamometer works. Okay. Third type of dynamometer is called hydraulic dynamometer. So hydraulic dynamometer means that the energy that is being generated by the engine is dissipated in water. Okay. So this is also very simple. You see, this is the shaft here. This sky color device is the stator, that means it is fixed. Okay. And what you have here, red color is the rotor, it rotates, but the design is such that, you know, such a tubular structure exists between the rotor and the stator on both sides. Okay. So one side is connected to water, so when the rotor starts rotating, you will have such water circulation, such eddies will be generated, water eddies will be generated inside that tubular structure. Okay, so all the heat, all the energy which is there in the rotor will now be dissipated in this, and water will be vigorously moving inside this, and when it starts vigorously moving, it will get heated up. A lot of energy will be dissipated because eddies dissipate a lot of energy, right. So this water will get heated up, and then, you know, from here you will take the hot water out. Okay, and here obviously you can put a tachometer which will read the RPM, and this stator, what you do is, stator you put some kind of a torque meter, so you measure the torque directly. Again, for measuring the torque, basically it's the same thing, you put a load cell and you put how much force is being exerted, and you know from the center how much is the distance. So basically you put a load cell and you can figure out what is the radius and multiply them to get the torque. That is what a torque meter does. Okay? So the hydraulic dynamometer works on the principle of dissipation of power in the fluid friction rather than dry friction. One of the problems with the earlier two dynamometers is it is a dry friction. So dry friction, if it gets heated up, first it is affected by temperature. If you are using a fluid, at least you can, by controlling the flow rate, you can make sure that temperature remains under control. So the friction does not change. Okay? Coefficient of friction does not change. So in principle, its construction is very similar to that of fluid flywheel. It consists of an inner rotating impeller. This is the inner rotating impeller which is coupled to the output shaft of the engine. This impeller rotates in the casing which is filled by water. Okay? The frictional forces between the impeller and the fluid are measured by a spring balance which is fitted on the casing. Basically it measures the torque. The heat dissipated due to dissipation of power is carried by the continuous supply of working fluid. So you make sure that water is coming in and hot water is going out. Okay? The output can be controlled by regulating the sluice gauges. So you can control the sluice gauge. Basically you control the flow rate of the water and output can be controlled. Any questions on this? Okay, so again all the calculations etc. is same as the earlier ones. I mean that fundamental does not change. The last type of, it is not exactly the last type, I mean there are other types also, but one of the important ones that I wanted to discuss and which is very, very popular is called eddy current dynamometer. So here the principle is that, you know, instead of having water circulating, you have a coil which generates magnetic field and then you have a steel rotor. So when it operates in magnetic field, there are eddies that are generated in this stator. Okay, and those eddies are also dissipating the energy, right? And those are also, I mean the rotor also needs to be cooled and that way you can absorb the heat. So you can see here, this is the shaft, okay, and this is the shaft bearing here, this is the rotor, this is the rotor part, you can see this here, side view. This is the shaft and this is the rotor, and here you have the coil. So this is the coil where you supply the current and it becomes magnetic, and this is the stator, outer body. So are you able to see this? So there is a coil, there is a stator, and then there is a shaft, and then of course there are bearings here. You have to support the shaft, whole thing. So the working principle of eddy current dynamometer consists of a rotor on which you have fitted a number of electromagnets. Electromagnets means, basically electromagnet means it becomes magnetized when you supply the current, basically a coil, okay, and a rotor disc made of copper coupled to the output shaft. It could be a copper or it could be, you know, even some kind of a steel. Basically it should be good in generating the eddies, okay. So with this the rotor rotates, eddy currents are produced in the stator due to magnetic flux set up by the passage of the field current in the electromagnets. These eddy currents are dissipated by producing heat. So basically there is a lot of heat generation. So once there is a lot of heat generation, what you do? You again put water through this entire casing while making sure that, you know, the water is, the coil is not affected. So there is current, but you make sure that current is not affected by water, and then you remove the water which goes with the heat. So you put cold water, hot water comes out. The load is controlled by regulating the current in the electromagnet. Suppose the engine is generating more power and you need to absorb more power. So what you do is you supply extra current. When you supply extra current, more magnetic force is generated, more eddies are generated, and more eddies will dissipate more amount of energy. So, whatever power is being generated by the engine will now be dissipated in heat. So, the current in the coil, if you have to absorb more amount of power, you increase the current. If you have to absorb less amount of power, you reduce the current. Okay? What is the advantage? High brake power per unit weight of the dynamometer. So, the eddy current dynamometers are actually the smallest specific weight devices. In very small volume, you can absorb lot of energy compared to the earlier three that I have described. They offer the highest ratio of constant power speed range. Okay, so they are pretty good for constant power speed range. Level of field excitation is below 1% of the total power being handled by the nanometer. So, the current that you are supplying from outside is actually minuscule. It is only 1% of the power which you are trying to absorb. So, it is not really a parasite on the electrical power. Okay. So, development of eddy current is smooth, hence the torque is also smooth and continuous under all conditions, and this is relatively higher torques which are typical of engine at low speed. They can also be absorbed very effectively by this device. It has no intricate moving parts except shaft bearings. So, the only failure that happens in this engine is that the bearings sometimes after 5, 7, 10 years can go bad, otherwise it is a pretty sturdy device. And there is no natural limit to size, either small or large. You can make eddy current dynamometer for very small engines such as your RC planes of 5 cc, you can make eddy current dynamometers. And if you want to make a ship engine of 80 megawatt, you can even make the dynamometer for eddy current dynamometer for that as well. So, this is one device which can cater to the entire spectrum of applications. As small and as big engine you can make, you can use this particular device of the same size for testing of that particular engine. There is something called swinging field dynamometer or DC dynamometer. So, basically swinging field dynamometer, there are two dynamometers, one is DC dynamometer, the other one is AC dynamometer. Swinging field dynamometer is a DC shunt motor, so supported on trunnion bearings to measure that their action torque, that the outer case and the filler oil tend to rotate with the magnetic drag, hence the name is swinging field. The torque is measured with an arm and weighing equipment in the usual manner as the earlier ones that I have described. This dynamometer is reversible. The best part of AC and DC dynamometer, if the dynamometer is based on DC motor, then it is DC dynamometer. If it is based on AC motor, then it is AC dynamometer. The best part of AC and DC dynamometer, which are both swinging field dynamometer, is that what is happening in the earlier four that I have described is that the engine is generating power and it is being converted to heat, and then it is thrown out. In these two, what happens is, and those are not motoring. Suppose you have to start the engine, you can't. Okay, but for certain applications of the engine, you also want the engine to be rotated. If it is a large engine, you can't really crank it by hand. Suppose you are asked, okay, 100 horsepower engine, can you crank it? It's not possible. So there these swinging field dynamometers come very handy. They have this very beautiful property that they can act as motor as well as generator. Okay, so if you have to start the engine, they can act as starting motor, and once the engine is started and you need to absorb the power, then they will absorb the power, then they will start acting as generator, and they will generate electricity, and that electricity can be really fed back into the grid. Of course, there has to be appropriate electronic measurement so that you don't pollute the power in the grid. Pollute the power means you have to match the sine wave. If the sine wave of the electrical power from the power plant and your sine wave, if it is not matching, then you will be creating pollution of the power, right? Sine waves have to match perfectly. So using appropriate electronics, you can do that. Okay, so So this is AC and DC dynamometer. It is reversible. That means it works for motoring as well as for power absorption devices. When used as an absorption dynamometer, it works as a DC generator and converts mechanical energy into electrical energy. And when you are using as a motoring device, that means external DC voltage is needed. It works as a motor and it starts the engine. And this load is controlled by changing the field current. Okay. So these are AC dynamometer, DC dynamometer. AC dynamometer is also called transient dynamometer. Okay, it's transient dynamometer. What is the meaning of transient dynamometer? See, you must have seen that all these dynamometers which I described, there is a certain load and certain speed which is fixed, and you can measure the power output. But you know, if you look at the modern emission regulations, what they are saying is that measuring the power or testing the engine only at a certain load point and certain speed point is not representative of the emission it generates in the real life. In the real life, if you have to operate a car, how do you operate a car? You start the car, very slow speed, then you take it you put it in reverse gear, take it out of the garage, apply the brake, then you go 100 meters, then there is a turn, you slow down, then you accelerate, you come to the main gate of your colony, you are at 30 kilometers an hour. Then there is a red light, you try to enter the traffic, okay, then you stop again. Then you go into the main road, you run at like 50 kilometers an hour. Then you go to highway, there is again stop, there is a horse cart coming on your way, there is a dog coming on your way, the other guy is deaccelerating. So in real life, you know, all the time the torque requirement, the speed requirements, these are the speed, these are changing. So if you're just testing the engine at say 2000 RPM, 50% load or 75% load, is it going to be same? Is it going to be reflective of how your engine is behaving or how the pollution it is going to create? No. So for that, you know, depending on the driving habits of the people, there is something called driving cycle for a particular country that is developed. So driving cycle means it tries to capture the typical behavior or driving requirement of a people of a particular country. In fact, if you look at BS6 and Euro 6 norms, we have not adopted Euro 6. Why? Because Euro 6 is depending on European driving habits where the roads are clear and the maximum speed can be up to 120 kilometers an hour. Can you drive at 120 in India? It's not possible. Even on Lucknow-Agra expressway, it is challenging, and it is only built a couple of years back. So that's why what we did was that when we developed our own emission norms, we copied the numbers, but we changed the driving cycle, and we included the Indian driving habits, Indian speeds into it. So that's why in BS6 norms, or even for BS4 for that matter, the maximum speeds were limited to 90 kilometers an hour, because that is what is more typical to us, right? And if our driving habits include more driving between say 20 to 40 kilometers an hour, suppose, that should be reflected more here. The weightage should be more. So this lower end speed needs to be changed all the time, and this cannot be done by eddy current dynamometer. This can only be done by transient dynamometer, which is AC dynamometer. It can change, you can specify, and it can change the testing accordingly, change the testing requirements accordingly. Okay, so is that clear? Fan dynamometer is also another type of dynamometer. This is also absorption type dynamometer. It is mainly for rough testing and running in. Running in means, what is running in? You buy a new car or a new engine which is just out of the production line, and you want to run it for say 50 kilometers or say 1 hour. So you put it in the engine, run for 1 hour, and then pass it. So the accuracy of fan dynamometer is extremely poor. You don't need very accurate at the end of assembly line. Okay, the power absorbed is determined by the previous calibration of the fan brake, and this is how it looks like. Okay, then there are transmission type of dynamometer, as we mentioned. So this is all about absorption type. Transmission types, also called torque meter, consists of strain gauges which are fixed on the rotating shaft. Torque is measured by angular deformation of the shaft, which is indicated as strain on the strain gauge. It has usually a 4-arm bridge, you know, Wheatstone bridge, okay, which is used to reduce the effect of temperature to minimum, and the gauges are arranged in pairs such that the effect of axial and transverse load on the engine stage is avoided, and this is how it looks like. This is the input shaft, power is going out and you have applied the torques, I mean the strain gauges, okay. So these are applied and you can measure the deformation of the shaft. We do not use the transmission type of dynamometer for engine testing that much. What we use is the chassis dynamometer. What is chassis dynamometer? So you have to understand, this is something that you will hear very frequently. If you are testing an engine, you have made an engine, that will be tested on engine dynamometer. So if you are testing on engine dynamometer, you have to represent the emissions as grams per kilowatt hour, because you are measuring the engine power output. But suppose if you want to measure the emissions from a vehicle, in a vehicle, do you know how much power is being generated at 20 km an hour, 30 km an hour? No, it is not possible. Those are measured by chassis dynamometer. That means you put the entire vehicle and test it, and there the emissions are represented in the units as grams per mile or grams per kilometer. So whenever you see the difference, if the emissions are shown as grams per kilowatt hour, that means immediately you will understand that this is engine testing and it is put on some kind of a absorption type of dynamometer, okay. And when the units of the emissions are grams per kilometer, that means you are talking of the testing of entire vehicle. How it is done? So in order to test the complete vehicle, a chassis dynamometer is used. Using of the chassis dynamometer allows the test engineer to simulate the road load conditions. I just mentioned to you that, you know, all those conditions, you come out of your house, go out of the garage into the main street, then into the main road, then onto the highway. All that can be done by road load simulations using chassis dynamometer. You cannot simulate them on engine dynamometer that easily. It is termed as all weather road for test vehicles. So all weather road for test vehicle means even if it is snowing outside, you can create controlled conditions inside the test cell and you can test your vehicle. The road load on the vehicle can be put on the engine on a chassis dynamometer, and quick results can be obtained. However, this dynamometer is quite expensive. So we are trying to install a chassis dynamometer for a two-wheeler, and this will be costing quite a lot, certainly not in lakhs. And if you want to do it for the car, for example, it will require a lot of space, and then it will also require a lot of money, several crores of rupees. How it looks like? This is like this. So what you do is, you basically, there is a car or whatever vehicle you want to test, and the engine is here. Engine drives only the front wheel, so you put that on a roller, okay, and then you tie this car. Make sure that it is completely immobile, because if it moves, that will be disaster. So only the wheels will rotate, and against that, you know, this roller will also rotate. And then, you know, when the vehicle moves, there is air coming in front, but right now your vehicle is stationary. So if you don't provide that air at the same velocity, it will be disaster, right? So you put a big fan which also rotates with the same speed as the speed that you are simulating. So that much air velocity should come in, okay. And here you have the dynamometer, I mean the AC motors. And then you will have a driver sitting, and there will be a panel in front of him which will display how much is the speed he should have and how much the actual speed he has. So depending on that, he will try to match the two numbers, and that speed will change according to the driving cycle, okay. And then of course what you will do is, you will take the exhaust gas, put it through the PM interface and measure the PM, and then of course you will measure the different regulated emissions using such an analyzer, and do whatever test you want to, but this is the heart of the system. So you can look at performance, emissions, fuel economy, particulate measurements from a particular vehicle. So nowadays, you know, whatever cars are coming into the market or even two-wheelers that are coming into the market have to necessarily meet all the testing on the chassis dynamometers in order to comply with all the performance and emission regulations requirements, even the fuel economy requirements. Okay, so I think now I must stop here.